So section 1, review of computing systems without GPUs. That's to see we are going to have a review of computing systems. We are going to have a review of CPU computing systems. The main target of these slides is to understand the GPU computing and the GPU computing systems. But we start with the CPU computing systems. The computing systems without any GPUs, because the basic concept comes from CPU computing systems. It is going to be used again by the GPU computing systems. So it is going to make it easier to understand if we can do a review of the traditional CPU computing systems. That's the reason why before we dive into the GPU computing and the GPU computing systems, we do a review of the CPU computing system. Okay, we won't go through every technical details of the CPU computing systems. We are going to just go through a few topics. Mainly, we are going to go through the parallel programming paradigms. We are going to have a look at this MPI parallel computing. Mainly, we are going to have a look at this MPI parallel programming paradigm, and then the OpenMP parallel programming paradigm, and then the mix of the two, the MPI plus OpenMP parallel programming paradigm. We are going to go through these three main topics, and we are going to find out that the GPU computing, they didn't reinvent the wheels. They reused the basic concepts of these computing systems, and they develop their GPU computing system. So we are going to go through these three topics. And then besides that, we are going to have a look at this NUMA domain definition, also called NUMA nodes, because this concept has been reused also by the GPU computing systems. And we are going to also have a look at these multiple NICs per physical node, because for GPU computing system, it's always multiple NICs per node. Okay, this is the main topics of this section 1. Okay, before we start, here is the copyright disclaimer, is that I have put a lot of contents from the internet to do these slides. Whenever I have done that, I have put the links of the content at the bottom of the slide to show where is the source of the content and who is the copyright owner of the resources. Okay. So very first, we need to have a look of this MPI programming paradigm. Okay, somebody call it MPI programming model, but I prefer to call it MPI programming paradigm. That's the same thing. Okay, maybe just by start, we start by have a look of this mathematics behind this piece of code. Basically, what this piece of code is doing is calculating the integration. And suppose you have a curve, it's like that. And this is starting point is A, and this point is B, and you need to calculate the integration of this curve. Okay, the integration of this curve. And now, if we have just one CPU or just one server, you just do your programmer and it's going to work. You are going to calculate that one. But the fact is that for our discussion, what we are going to do is that we are going to use we are going to use n nodes, totally n nodes to calculate the integration. If you have n nodes, what we are going to do is that we are going to ask each node to work on a piece of the workload. So here we start from A, we divide the workload into pieces, into multiple pieces. And then the last one is n minus 1, sorry, n minus 1. Sorry, I need to do it nicely, so I need to commit. So what we are going to do is that we are going to, the last piece of workload is n minus 1. The first one is 0. The second one is 1. The third one is 2, etc., etc. We are going to follow the C scheme, starting from 0 to n minus 1. This is the pieces that each node is going to work on, because you have n nodes, you want the n nodes to work on this piece of workload. This is the mathematics. But basically what we have as the computing system is like this. You have a node. On the node, you have a processor, which is P, and you have the cache connected with the processor, and then you have the main memory, which is M. At the end, because it's a network, you need to have a network interface, and you are connected to the communication network. Okay. And then for the node 1, for node 2, for node 3 is the same thing. All the nodes are connected to the network. Okay. This is the network. And basically, if node 0 is going to work on this piece of workload, this is for node 0, okay, is for node 0, and then it's going to calculate its integration. The integration is going to be called psum by each node, and it is going to be stored in their memory. At the end, because you have multiple psums, if you have n nodes, you are going to have n psums, and the result, the final result, is the sum, which is the sum of all the psums. So is the sum of all these psums. Okay, so from 0 to n minus 1. This is the mathematics for this piece of code. Okay, this is a piece of Fortran code. It's not difficult to understand. We just need to go through it. We just need to read it to understand. Okay, for MPI program to work, the first thing is that the program, the MPI program, they need to call a function which is called MPI, initialization. So here, after you have defined this integer dimension, etc., basically before the two calls, we have two calls here. Before the two calls, you need to have another call, which is call MPI initialization, which is a functional call, which is called call MPI initialization. And after you have done your work, before the program could be stopped, you need to call another function, which is called call MPI finalization, finish. This is the last function for MPI code to call to finish this this calculation. Actually, let's just try to understand this MPI initialization and the MPI finalization. The MPI initialization is to set up the communication scheme between the n computing nodes. Okay, and then you can understand this, the last functional call MPI finalization, MPI finish, is to destroy this MPI communication infrastructure. So you set up this infrastructure before you can use it. After you have used it, you need to destroy it. So you need to have these two functional calls for this piece of work, piece of code to work correctly. Okay, fine. We have this done, and then we need to understand this is the piece of code. This piece of code is going to be executed by each node. We are going to have only one process per node. So when we are talking about MPI programming, we always use the word process. So process 0, process 1, process 2, etc., etc. Okay, we always use process. Suppose we have only one process per node, and you have n nodes, you are going to have n MPI processes. Okay, and then we have two functional calls, MPI com size and MPI com rank. And what these two functional calls are doing is that they need to find out the size of the MPI communication infrastructure. The size for our particular case, the size will be n. Basically, the size is the total quantity of the nodes, or we should say it more precisely. That's the total quantity of the MPI processes, because there is a case you can have multiple MPI processes per node. So this is size is the total quantity of the MPI processes, and then the other one is the rank. The rank, you can understand, is the ID of the MPI processes, because you have here, you have n MPI processes. If you have 1,000 or 10,000 MPI processes, you need to distinguish them. What you can do with that, you give each process an ID, and basically the ID is a number. The ID is the number. Is the MPI process number. So you have 0, 1, 2, 3, and you set up this MPI communication infrastructure. You are going to call these two functions to find out how many MPI processes we have for this particular running of the code, and what's the ID of myself. And just remember that each node is going to run the same piece of code, and then each MPI process is going to know the total quantity, and it is going to know its own ID. Okay, this is the first step. You set up this MPI communication infrastructure, and then the next step, basically, it's very short, but actually it could be very complicated. I have learned that there is a particular project. The decomposition has been done in 8 years. In 8 years, there is a PhD student just there to do this decomposition. Decomposition means that you have a computation task, and you need to break this computation task down and ask each MPI process to work on a piece of the workload. You have a huge workload, you have a big workload, you need to have multiple MPI processes, and each one is going to work just on a piece of the workload. For our example, it's very simple. Okay, here the workload, as I have drawn here, is from A to B. Okay, and then because we know we have, this is the total quantity of MPI processes, and the total workload is B minus A. So we divide the total workload by the total quantity of MPI processes. We know the workload of each MPI process. Okay, and then we are going to ask we are going to use this formula to calculate each MPI process the, the workload. How is that going to be done? This is the workload from A to B. So for process 0, now is going to use this formula to define a starting point. Its starting point will be my A, and is going to be to use this formula to define its ending point as its workload. So the ending point for each workload is my B. And the piece of workload for MPI process 0 will be from my A to my B, and it's like this. And we use the same formula. We are going to find out for process 1. Here, this is process 1. Process 1, my A for process 1 will be A plus B minus A. Okay, and A equals B. Sorry, divided by N. Sorry, I need to do it nicely. Let me bring my, let me bring back my GOM. Okay. So it's done, and we need to bring back my pen. So for the second MPI process, its starting point will be my A divided by N, and its endpoint is going to be my B. Let me write here. My B will be my B will be my A. That's my A plus my A is like this, B minus A divided N divided by N plus B minus A divided by N again. So the final result for my B is going to be 2 times B minus A divided N. So this is the my B for the MPI process 1. So this is the formula, and then each MPI process is going to use these 2 lines of code to calculate their my B and their my A. And each MPI process afterwards, each MPI process is going to have their my A as the starting point, different from the others, and their my B will be the ending point. Each one is going to have a different one. And the final result is that we are going to have each MPI process, they are going to find out their starting point and ending point, and each MPI process is going to find out its own workload. So each one is going to know where is its workload. The last one is this one. They are going to know where is workload. Each guy is going to have their my A and their my B, their starting point and ending point. So this part, basically, from the MPI programming point of view, this is the computation decomposition. You have to decompose your computation task. For us, this is very simple. Is that it has been done by these 2 lines of code. Okay, after each MPI process, they have found out their workload. They are going to work on their workloads. They are going to call this function integrate my A and might be to calculate their own p-sum. Okay, this is going to be done by each MPI process. After the p-sum has been found out, is going to be located in the main memory. Okay, so each MPI process is going to have the p-sum, and the p-sum will be in the memory. Well, you can call this one p-sum 0 because this is by MPI process 0, and this is 1, this is 2, etc., etc., and this is p-sum n minus 1. That's possible. You can call it this way. But the point is that the final result, what I want to have is the sum of all these p-sum of the MPI processes. Okay, now just try to understand this p-sum stands for partial sum. So what I want to have is the total sum. So we need to put all these p-sums together. How should we do it? Here, one way of doing that is this one. Let me just change a color. One way of doing is this one. We start from the if, and then the else, up to the and if. Okay, this is the piece of code to find out the sum. To find out the sum, which is the sum of all these p-sum. So what this piece is going to do is that we just need to read through this one to understand. Okay, so right now there is a note here is that run 0 is going to collect partial results, is going to collect p-sums. So here, each MPI process is going to go through this line of codes. So the first one, we are going to go through this if. If rank equals 0, that means if I'm rank 0, okay, if I'm rank 0, what I'm going to do is here. What I'm going to do is here, I'm going to define a result equals p-sum of myself, because right now I'm rank 0. So this is basically this is p-sum 0. You have here p-sum 0. It has been put here, and then afterward I'm going to receive the p-sums from all the other MPI processes. I'm going to start from 1. So I'm going to do a do loop. I'm going to start from 1 till the end. The last one is size minus 1. Start from 1 to size minus 1. All these MPI processes, I'm going to receive the p-sum from them. Okay, so I'm going to call MPI receive. I'm going to receive the p-sum. I'm going to put this p-sum in the temporary, in this variable. So I'm going to receive MPI double precision. So I'm going to start from the first I'm going to receive from MPI process 1 the p-sum, and then just let's read this one. Okay, this is the call. This is the ending of the call. Basically, the functional call is a loop. It's a loop, and the MPI process 0 is going to receive one by one from all the other MPI processes the p-sum, and after it has received the p-sum, is going to sum up the p-sum and is going to put it in the res, the result, in the result variable. The res is result. Okay. Okay. That's for rank 0. If I'm not rank 0, because there is only one rank 0, all the others, what they are going to do? Okay, if I'm not rank 0, the rank 0 is going to run this one, and all the others, they are going to do something else. Let's change color. All the other ranks, all they are going to do is here. All the other MPI processes, what they need to do is call this function MPI send. all the other MPI processes, they are going to send their PSUM to MPI process 0. So I'm going to send my PSUM to rank 0, and I'm going to send a double precision number. And this is a call, functional call, to call the MPI send, to send the result to MPI process 0. Okay. After this if else and if this piece of code, this block of code, after it has been done, the final result is that we are going to have rank 0, which is holding this result, which is the final result, and is the sum of all the p-sums. Basically, this is what we want to have. That means at the end, what we want to have is the result, which right now is holding by MPI process 0. Okay, so then MPI process 0 need to write this result somewhere. What I mean here is the output. The MPI process 0 need to output the result, and then the job has been done. The running of the code could be terminated, and is going to be terminated. Okay, this is a piece of very simple MPI code. It's very simple, but it has the main components. I mean, it has the main blocks. It has the main blocks as MPI program. The first one is that you need to set up the MPI communication infrastructure, and then each MPI process need to get the basic information for them to coordinate each other. And then the third step is that you need to do the workload decomposition. And then each MPI process is going to work on the workload. And at the end, each MPI process, they need to, the MPI processes, they need to exchange the results to find out the final sum. And then the result need to be output somewhere. Print on the screen or output into a file. This is the basic functional blocks of an MPI program. This is simple, but it has the main MPI. It's very simple. It has the main functional blocks of MPI program. Okay, this is a very simple program. I would like to stop here. This is enough for us to continue our discussion. I just want to reset up the MPI communication programming paradigm, and this was this model for this kind of MPI program, MPI programming. What's this? What's the model and what's the paradigm? And just to reiterate all this, to make sure you have this as a foundation to continue our discussion, because this is later on will be used when we are going to discuss the GPU computing, and we are going to take it for granted that you have this kind of concept in your mind. Okay, we stop here. We are going to have a rest, and then afterwards we are going to continue. So I stop now.